Hello and welcome to The Naked Scientist with me, Chris Smith, and with Kat Arney.
This week, we're donning our body armour and heading out into the battlefield to uncover the science behind warfare. How do explosives work, and what can we do to protect against them?
Plus, the science headlines from across the world, including are antibiotics making us fat, the comet that may have a cave inside it, and how to spot when your partner is ovulating.
The Naked Scientist podcast is powered by ukfast.co.uk.
First, millions of doses of antibiotics are administered every day, particularly to young children. While their life-saving benefits speak for themselves, could there be a downside to antibiotic exposure in early life? A new study on young mice suggests that use of the drugs might be making children more likely to become obese and causing lifelong changes to metabolism. From the NYU Langone Medical Center, Martin Blazer.
I realized that farmers give antibiotics to their farm animals to improve their growth. And about 10 years ago, a light bulb went off, and I thought, maybe this is what we're doing to our children. We're causing them to grow more, too. So in recent years, we've done studies in mice where we've given the mice doses of antibiotics at the levels that farmers give. These are low doses given every day in their drinking water, and we found that the mice become fat. When we put them on a high-fat diet, they become fat. When we put them on antibiotics, they become fat. And when we put them on both together, they become very fat. But human children aren't getting low doses of antibiotics every day. They're getting pulses of antibiotics to treat their ear infections and their throat infections. So now we developed a new model, which we call PAT, for pulsed antibiotic treatment, so that we're mimicking the kind of exposures that children get.
And you're asking, does this pulsed administration of antibiotics, which is more similar to what we do in real life, does that also translate into subsequent changes in growth, including obesity?
Yes, so we're asking whether these pulsed doses of antibiotics, mimicking the kinds of doses that kids get, will they change metabolism? Will they change the development of the mice? And will they affect the microbes that are living in the mice?
What happens?
Well, not surprisingly, the antibiotic administration affected the populations of microbes in their body, and this is what's called the microbiome. The antibiotics changed their diversity, how many different kinds there were, and they changed the composition of the community so that the mice had different kinds of communities when they were on antibiotics. And importantly, the effect lasted way beyond when the antibiotics were stopped. In some cases, they continued into when mice are in middle age, even though this was given to mice during their childhood period.
And what effects were there on the mouse metabolism and growth and other important things that we were aiming to find out what would happen in children?
We found that the antibiotics had effects on their metabolism. And here we used two different antibiotics, amoxicillin, the most widely used antibiotic in childhood, and a macrolide antibiotic. That's the second most widely used antibiotics, and they differed a little in their effects. The mice on the amoxicillin developed bigger bones. The mice on the macrolide, they developed more fat.
Can you explain why giving antibiotics should affect the composition and growth of bone in one case and becoming more fat in the other case?
Well, we're not entirely sure what accounts for the differences in responses to the antibiotics, although in our past studies we've seen effects both on fat and on bone. And so we're actually, that's an area that we're currently working on to understand the intermediate mechanisms that account for this.
But the fact that the effects were lifelong is really quite worrying, isn't it? Because that's saying that if you administer antibiotics, as we commonly do to many, many children when they're little, you are potentially distorting or bending the composition of the bugs that live on them and in them, and that will have metabolic consequences that could last their lifetime.
Yes, in our earlier paper, we showed that if we gave the antibiotics and we perturbed the microbes, even for a short period of time, there could be lifelong metabolic effects. Even when the microbes went back to their usual compositions. So we are concerned about this, and in a sense, we're recapitulating what the farmers have been showing for decades. And they show the earlier you start antibiotics, the bigger the effect of growth. We're finding that too.
Now, doctors are not going to take away from this the message, don't give children antibiotics, because in many instances, antibiotics can be absolutely critical in a life-threatening situation. But what could we do to mitigate these effects then?
Well, your point is really good. Antibiotics are necessary drugs. They have saved countless numbers of lives. And in no way am I saying we should abandon antibiotics. We just need to use them more judiciously.
And extrapolating your findings, albeit in mice, to young kids, are we therefore presupposing that some of the growing trend in overweight amongst youngsters could be attributable to overuse of antibiotics?
Yes. Our study was a study of mice. It's our third study of mice, all showing that early life antibiotics are changing development, increasing body mass. And there now have been several epidemiologic studies of groups of children. The Avon longitudinal study that we participated in, showing that kids exposed to early life antibiotics had increased markers of obesity or adiposity or fattiness at the age of 7. So there's a growing body of data in children as well that antibiotics have cost in terms of obesity. There are studies about antibiotics in asthma and food allergies and celiac disease. So we're coming to realize that antibiotics have great benefits, but they also have some potential costs.
Serious food for thought there. That's Martin Blaser, and he published that work this week in the journal Nature Communications.
It really does put a new spin on the whole phrase, you are what you eat, doesn't it?
It certainly does.
Now, every summer, the Royal Society in London comes alive with a week-long exhibition showcasing the very latest in cutting-edge science from around the UK. And this year is absolutely no exception, with exhibits and events covering everything from nanotechnology to cosmic rays, cancer screening and fighting the flu. Kat went along to talk to a few of the researchers presenting their work.
Hi, I'm Philip Murgatroyd. I'm from the University of Birmingham and I'm part of the Stonehenge Hidden Landscapes project.
There's a wonderful exhibition here. We've got a tray of sand. There's an enormous flat iPad-looking thing, a very bizarre piece of machinery, the Gravity Imager, and it's all done up as an underground station. What is this about?
The basic theme of the display is Stonehenge Underground because it's developing from work that we've done using archaeological geophysics in the Stonehenge landscape, and its modern scientific techniques have allowed us to completely revolutionise how we see the Stonehenge landscape.
I have to ask, what on earth is a Gravity Imager? That looks a very impressive piece of scientific kit, but what does it do?
It's part of the future of geophysics. We're working with the GG-TOP project at Birmingham and they're developing a new way to detect gravity by using an atom interferometer. Basically, this catches a cloud of atoms in a vacuum and throws them in the air and sees how they go up in the air and come down using a laser interferometry. And because we're detecting the effects of gravity on very small atoms, we can detect very small influences of gravity. So we can detect smaller objects based on their gravity than we were ever able to before.
So that's letting you see what's underground, what's in the ground?
Yes, the whole reason we use different types of geophysics is there are different things you can see with different types of geophysics. Currently, gravity detection is quite poor for archaeological deposits, but that's because the sensors aren't fine enough. By developing our own sensor, we hope to be able to introduce gravity into the whole suite of geophysics.
Tell me one of the most interesting things you found under Stonehenge using this kind of technology.
Stonehenge has actually been very well surveyed because it's a relatively small area. Now, what we've done in conjunction with the Ludwig Boltzmann Institute in Austria is they've developed a suite of technologies that allow us to collect geophysical data pulled behind quad bikes at 70 miles an hour. And this allows us to not just focus on areas where we think there are stuff, but focus on the whole landscape. We've done 12 hectares of magnetometry, and that allows us to see everything. We can see the spaces where we assumed was spaces between monuments, and we found that they're not spaces at all. There are monuments there, and we've just never looked for them because we've never had the technology to do so.
So there's a whole world that's underground that's being revealed by new technology.
Yes, absolutely. It's an entire landscape that we've not been able to look at geophysically before, that now we can, and it's opened us up to a whole array of different monuments.
Hi, my name is Matthew Morris. I work for University of Leicester, and we're here explaining how we were able to identify Richard III's remains.
Now, there's a huge glass case here with a skeleton in it. Is this the man himself?
It's a copy of the man himself. So we've reburied the real king in Leicester. But this is an exact 3D printed copy of his skeleton that we made from the CT scans that were made of the real bones. We've then created models that we've then printed out using a 3D printer.
So Richard III was very famously found in this car park in Leicester. What can people see here to help explain and understand how you went about identifying whether it was our missing king or not?
So we've got the skeleton himself. We're explaining how we were able to put all the evidence together to make the case. So it's like a 500-year missing persons case, mystery case, and we're putting it together. We've got activities about statistics and probabilities. We've got an arrow drop. We've got a medieval knight, so we can show people how the injuries were inflicted on the skeleton that we've got.
There has been some discussion about whether it really is Richard III. How do we know that it definitely is?
So that's what we're here to show people how. So you can't prove it's Richard III from one strand of evidence, but when you take all of the strands of evidence together from all the aspects of the investigation, you come up with a probability of 99.999% likely that this skeleton was Richard III. And so that's what we're here hoping to convince everybody.
So what's this arrow drop? It's like looks a bit like a guillotine. Can we wind it up and have a go?
We can.
All right, let's give it a go. Go! Whoa!
So I'm Patrick Naylor. I'm at Imperial College in London, and we're working on 3D sound and soundscapes, particularly focusing on how do humans understand sound and what can we learn from that to help us design machines that understand sound better than they do now. In here we have the opportunity to talk to our robot. Hello.
Hello, it's nice to meet you.
This is a 50 centimetre high robot that is running a number of processing algorithms. First of all, it's doing face detection, and it's also working out the direction that sound is coming from, and it's following that by head tracking.
He's a charming little chap. I feel like I want to wave at him. He's white with some nice orange styling, tipping his head towards me. What's going on here?
The sound is being picked up by the microphones on the head, and from these two signals, from the two microphones, the robot works out the direction that the sound is coming from. From the cameras, it works out the position of faces using face detection algorithms, and the robot tries to pay attention in particular to directions that have sound coming from them and also a face is detected. So faces that talk are important to the robot because that's where its instructions will come from.
What would be a kind of application of this? How could this kind of technology be useful? Oh, hello, he's looking at me while I'm talking.
Oh, yes. It's all about human-robot interaction. So any robot interaction involving humans, it's likely that speech is going to be important. And in real-world environments, robots have to deal with multiple humans in the same room. A typical application which is quoted is a welcoming robot for a hotel. You walk up to the check-in desk, and instead of having to queue up in line to check into your hotel, the robot might simply welcome you and give you your check-in details and your room key. Now, the important thing there is that there are many other people checking in at the same time. Which person should the robot pay attention to? So this selective attention, we call it selective attention, is an important capability that robots need to be taught, or we need to develop algorithms that can deal with that. Goodbye.
It was nice to talk to you. Had fun at the exhibition.
That was so cute. That was Patrick Naylor and his robot, and before him you heard Matthew Morris and Philip Murgatroyd.
This is The Naked Scientist with me, Chris Smith, and also with Kat Arney. If you'd like to get in touch, it's chris@thenakedscientist.com. You can tweet @nakedscientist, or you can find us on our Facebook page. We love hearing from you, Thoughts and feedback most welcome.
In August 2014, after 10 years in space, the European Space Agency's Rosetta probe successfully rendezvoused with comet 67P Churyumov-Gerasimenko. Yes! This duck-shaped ball of ice and dust is hurtling along at nearly 120,000 kilometres per hour on a course towards the inner solar system where we are. Rosetta is keeping pace with it and using its onboard instruments to observe the core or nucleus of the comet as it warms up during its approach to the sun.
The data, including some stunning images that Rosetta is beaming back, are now being analysed. One observation that's caught the eye of the mission scientists, though, are some bizarre circular pits. They're each about 200 metres across and they're peppered in small clusters across the comet's surface. They suggest, the team say, that the comet might contain caves.
Colin Snodgrass is a comet specialist with the Open University, and he's been taking a look at the new findings for us.
It's a very strange shaped comet. It's got sort of two parts, and early on it was kind of described as this rubber duck shape with a head and a body. And this is still useful to think about because it naturally lets you imagine the shape. And the particular thing we're looking at here is on the kind of the back of the duck. There are these large pits, up to a couple of 100 meters across. And these are sort of strange. They don't look like craters that you find on the moon or on asteroids. They are holes that seem to go into the inside of the comet.
How big is the comet itself?
The comet is about 4 kilometers across, so the solid body of it is pretty small. When you consider that comets that we see in the sky, actually they're what are called the comae and the tails, the thin atmosphere stretches over tens of thousands to millions of kilometers, but it all comes from a very small central icy body that's only the sort of size of a small town.
And where do comets originate from in the first place?
A comet like this one, we think, comes from a region of our solar system called the Kuiper Belt, which is the area of the solar system where Pluto is. It's out in the sort of outer observable edge of the system. And it makes them very interesting because bodies that have been out there have kind of been in deep freeze since the time that the planets formed. So what we're looking at is we're looking at a little remnant from the time of formation of the planets, a leftover building block, if you want.
And how does this comet happen to be coming past us only now, given that it dates from way back 4.5 billion years ago when the solar system formed?
Comets like Churyumov-Gerasimenko actually are only in the inner solar system for relatively short time on the age of the solar system, so maybe a few tens of thousands of years. What happens is that somewhere in the outer solar system, out by Pluto, a body like this comes close to some larger object, for example, and the gravitation effect of one of the larger bodies out there, like Pluto, slingshots small bodies in towards the inner solar system, and eventually they come in and then get into these orbits that take them closer to the sun, and then as they get closer to the sun, their ice starts to evaporate away and produce the tails that make them look like a comet as we know them.
And do you think that the same process could also explain these interesting pits?
That was one of the first possible explanations people looked at as well. We know that material comes from a comet. Maybe these are just eroded away, and we see that some of the activity of the comet comes from these pits. But the paper shows that if you do calculations, they can't just form by this way because the time that the comet is in the area near us in the inner solar system isn't long enough to have dug all of these pits. So the paper goes on to describe then they must have formed by collapse of material into the inside. So the idea is that these are sinkholes, that there's some spaces like a cave or a void inside the comet itself. And then what the activity does is it kind of weakens the surface enough until one of these collapses in to form these holes.
Do we have a stronger idea yet as to what this comet is made of? And even has anyone tried to weigh it so that we can begin to establish what might be in there or might not be in there to make these voids for the material to tumble into?
We have some ideas about this because Rosetta has been making measurements of the surface. And these pits are actually quite interesting because if you look at the walls of the pits, you see what we refer to as these goosebumps, or another phrase that was used was dinosaur eggs, which I quite like, which are these sort of balls a few meters across that make up the wall of the cliff. So possibly this pit has collapsed, allowing you to see the kind of building blocks inside. And in terms of weighing the comet, yes, we have been able to do that because we could measure the deflection of the spacecraft when it first arrived, caused by the gravity of the comet. So we know that its overall density is actually much lower than ice.
So that would fit with the idea that there may be cavities inside into which material could tumble and make these pits.
Yes, it definitely helps to explain it if we have these cavities inside, sort of like a Swiss cheese type model of the comet.
Colin Snodgrass talking us through the paper announcing those discoveries this week in the journal Nature.
Most animals, including humans, take steps to avoid finding a mating partner that is too similar to themselves. And in our case, this is with very good reason, because scientists have now discovered that people who inherit the same versions of certain genes from their mum and their dad, which can happen if you marry a close relative like your cousin, are likely to be shorter and to do less well at school than those people who get different versions of the gene from each parent. To find out more about this, Kat spoke to University of Edinburgh researcher Peter Joshi, who is part of the study team.
What we're doing is using modern genomic techniques to measure genetic diversity. And the way that we're doing that is that we're using 350,000 people in total to make sure that the study is very robust. We used 100 different populations across the world. With all of that information and then collating it centrally in Edinburgh, we basically had measured the genetic diversity of each of those individuals.
So you've got hundreds of thousands of people from populations across the world. How are you analysing their genomes? What are you looking at?
What we do is we look at the genetic diversity of individual people within that population and compare them with other people within the population. And at the same time, look at their cognitive ability, height, or blood pressure. And then within that population, see whether or not there's an association between genetic diversity and, say, educational attainment. And having done that, we then combine all of the results of the different studies to see whether or not the effect is robust and reliable across lots of populations.
So when you started looking at the levels of diversity, about whether people had 2 copies of gene or 2 different copies of a gene, what did you start to find?
We're looking at the whole of the genetic code of each individual, and we're scanning along that genetic code and checking what proportion of that genetic code is identical from the mother and the father. And what we typically find is that about 0.1% of the genetic code is inherited identical from the mother and the father. But that number varies from individual to individual. With some people it might be none at all, and in some other people it might be 3 or 4 times that. And what we find is that if you've inherited 2 or 3 or 4 times the norm in terms of lack of diversity, that reduces educational attainment, cognitive ability, and height.
So people who've got more similar genes from their parents, they don't do as well at school and they're shorter.
Yes, but it's also important to recognise that these effects are small. But on an individual level, it wouldn't be measurable. That's why we needed 350,000 people to sort of robustly demonstrate that it was a real effect. The mechanism that we think might be involved is that there will be things associated with development that might underpin growth and therefore your height. And so it's not height itself in a way that is being controlled in this way, but it's the sort of underlying biological systems. And 2 bad copies might affect height in that way and cognitive ability. And if that happens, if these traits are favoured by evolution, then we see this overall effect. Whereas for traits that are not subject to evolutionary pressures, we don't see that in quite the same way. It's speculation, and one of the things we want to look at in the next stage of our study, but it's to understand perhaps what's going on in more detail in terms of inheriting 2 identical copies of a defective gene.
That's Peter Joshi from the University of Edinburgh, and that study was published in the journal Nature this week. Now, it's not just embarrassment or blushing that makes a lady redden. Women also become subtly redder when they are ovulating, a new study has shown. Hannah Rowland.
About 10 years ago, somebody did some research on whether women changed in attractiveness across their ovulatory cycle, so their reproductive cycle. And he found that when women were ovulating, so when they were the most fertile, they were rated by male participants as more attractive. And so over the last 10 years, more and more research has come out showing that women's behaviour changes, their voices change, their odour changes, so they smell differently, and they're always more attractive when they're fertile. But in those 10 years, nobody's really got to the crux of why women are more attractive. And so we hypothesised that perhaps it was explainable by changes in skin colour. So chimpanzees and mandrills and other primates, when they're fertile, they have really obvious and conspicuous changes. So they get red bottoms and macaques get red faces. So we hypothesised that perhaps women also had redder, more attractive faces.
It's like a sexual traffic light then, although in this case red doesn't mean stop, it means go.
Absolutely. So red is a very attractive colour to us and to other non-human primates.
I see I've got a big red end on my microphone, so I wonder what that says about me. How did you do the study?
We had 2 undergraduate students who were our data collectors, and they recruited their friends to come and have their photograph taken. So they came every weekday, and we asked them personal questions about their fertility cycle, and we also asked them to use an ovulation test kit so that they could detect the hormones that signal when they're ovulating.
And what was the outcome measure apart from taking these pictures?
So we designed a programme to detect cheek patches and measure the red, green and blue colour of the photograph. So we then converted the red, green and blue using models from psychologists of how the human eye responds to colour, and we modelled how it would be perceived, how these cheek patches would be perceived by the human eye.
And can my eye tell when you're ovulating?
Really interestingly, we found that women do get redder when they ovulate, but it's just below the level detectable by the human eye.
Did you ask any humans, real humans?
No, that's the next step.
Doctors talk about a phenomenon called cloasma, which is when women have a high estrogen state, and they classically develop this during pregnancy, but also when they're using the oral contraceptive pill, because estrogen does change blood flow through the skin. Is this just because when a person is normally cycling, the estrogen changes are just a little bit less than they would be in something like pregnancy? So it's there, it's just too subtle for us to see.
You're right, estrogen's implicated in skin colour, but also women with higher estrogen levels have paler skin, and pale skin is very attractive in other studies. So actually when we predicted that skin colour would be the causation of this attractiveness, we thought it would be tied to estrogen. But when we map our colour change across the cycle, so it goes very low, it drops significantly during menses, and then rises rapidly towards ovulation and then stays high. When you map that onto the textbook estrogen cycle, it doesn't map very well. So estrogen peaks at ovulation, but it drops again just before menses. But our change in red actually maps basal body temperature much better. So there's probably a combination of mechanisms causing this subtle change in redness.
If it's not detectable by the average male, then what's the point of it?
Humans are sexually active across the month, across the year, whereas other primates are only receptive and only mate when they are fertile. And so there's a benefit to concealing ovulation in humans because it means that men are more likely to stick around and care for any offspring rather than, like you see in chimps, where males are only interested in receptive females and then go off and are more interested in the next receptive female. So I think ovulation is concealed in women, but there are these little bits of information, voices, odour, behaviour, leaking this information.
Hannah Rowland from Cambridge University, and that study is published in PLOS ONE. You're listening to The Naked Scientists with Kat Arney and Chris Smith.
Now, things are going to get a little bit more dangerous on the programme because we're going to be exploring the science now of warfare and explosions.
Right now, there are many wars and conflicts raging around the world, unfortunately, causing countless deaths and human misery. But warfare, sadly, is nothing new. Explosives have been used for over 1,000 years. Gunpowder is said to date from the 9th century. Its invention is usually attributed to Chinese alchemy, and it's often cited as one of the 4 great inventions of China.
Explosives are capable of causing catastrophic damage, but how do they actually work? And what's the difference between the gunpowder that the Chinese invented and much more modern high explosives? Ginny Smith went to meet Chris Bishop from Microsoft Research to explode some explosive myths and to find out how these chemicals do what they do.
It's a substance that's either a solid or sometimes a liquid, which can undergo a chemical reaction and can turn into a gas extremely quickly. And the gas occupies a volume about 1,000 times greater than the solid or liquid, and so it wants to expand very rapidly.
So all the different kinds of explosive work on that same kind of basic principle?
That's right, but the precise way in which that works can be very different for different kinds of explosives.
Can you give me some examples?
Well, the place to start, I think, is with the very first explosive, which is gunpowder, a mixture of charcoal and sulphur and saltpeter. The charcoal is a fuel, just like the charcoal on your barbecue. It can react with oxygen to produce carbon dioxide, and that releases a lot of energy. The oxygen, though, doesn't come from the air. In the case of gunpowder, it comes from the potassium nitrate. The potassium nitrate, we call an oxidizer. And when it undergoes this chemical reaction, the oxygen is released and combines with the carbon, the charcoal, and that produces energy.
So effectively, because the oxidizer's in the mixture, your fuel doesn't have to mix with air in order to burn like a candle, say, does.
That's exactly right. In fact, the burning process is much more rapid. We give it a special name. We call it deflagration, but it just means burning, essentially.
And do you have any examples of this that we could have a look at?
Well, we've got some modern gunpowder here.
It looks a bit like you've taken a pencil lead and kind of smashed it up a bit, so you've got little pieces of that pencil lead. You've got quite an impressive looking blowtorch there. You're going to use that to set fire to the gunpowder?
I am, but I'll just use a very, very small flame.
Well, that was quite pretty. We got a sort of whoomph and a bit of flame going up into the air.
So that's what we call a low explosive. So it burned quite quickly, just in a fraction of a second, because that's very good quality gunpowder. But there was certainly no bang. To get a low explosive to produce an explosion, it needs to be confined, so it needs to be trapped inside some sort of container. And so the pressure builds up until the point where the tube bursts, and that's when we get the bang.
So that's a low explosive. High explosives sound a bit more exciting.
So high explosives are very different in terms of the physics and often in terms of the chemistry. High explosives really were discovered in the middle of the 19th century. An Italian chemist, Ascanio Sobrero, was experimenting with taking various organic compounds and treating them with nitric acid. And one day he tried glycerine, and when he treated this with nitric acid, he obtained nitroglycerine.
How does nitroglycerine explode?
So the molecule has a carbon backbone, 3 carbon atoms in a row, and then attached to those are nitro groups, that's nitrogen and oxygen groups. And so the oxygen combines with the carbon within the same molecule. So it's a much more intimate mixture than even the world's best gunpowder, because these are mixed at the molecular level. And the nitrogen-nitrogen bond is one of the strongest bonds in chemistry. So it follows that when 2 atoms of nitrogen come together to make a nitrogen molecule, they release that energy. And so one of the big sources of energy in high explosives is the formation of nitrogen gas.
And have you got an example of a high explosive we could have a look at?
We could start by having a little look at some nitroglycerine. So I've got just a few millilitres of it to show you.
It looks like it's underwater and it's just a blob. It's colourless. It looks oily.
So this time, instead of initiating it using heat and producing deflagration, I'm going to hit this with a hammer. So we're going to provide a very sharp, hard shock. What happened then was a process called detonation, and it proceeds through a shock wave. In fact, it's a supersonic shock wave that travels through the nitroglycerine and causes the chemical reaction to happen. The chemical reaction releases energy, and that reinforces that shock wave. We now have a detonation proceeding at many thousands of meters a second, perhaps even up to 25 times the speed of sound.
So what does the shock wave actually do as it's propagating? How does it do its damage?
Well, if you were standing still and a shockwave went past you, what you would notice is a sudden rise in the pressure. So if you imagine you have something like a wall, at the moment it arrives at the wall, on one side you have high pressure and on the other side you have ordinary atmospheric pressure. Now, it doesn't take much of a pressure difference across a large area to produce a very large force, and it's that force which can push down a wall and do all sorts of damage. So here's another way of illustrating what we mean by a high explosive or detonation. I have something here called shock tubing. And it's plastic tubing. It's 3 millimeters in diameter. It's a bright yellow colour. It's got a 1 millimeter diameter hole down the middle. And the inside of that hole is coated in a very light dusting of a high explosive. It's called RDX. It's actually the most powerful, commonly used military explosive. But the quantities here are tiny. It's a few grams for every kilometre of shock tubing. The way I'm going to set it off is we need a shock to initiate the detonation.
So the equivalent of hitting it with a hammer?
That's right, but I've got a slightly more sophisticated way of doing it here. This is a so-called blasting machine. It's effectively a little electronic handheld device, and it's going to charge up a capacitor to 2,500 volts and then discharge the capacitor to produce effectively a little lightning strike. And that lightning strike is a very sharp, short release of energy that will initiate the shock wave that will then travel down this shock tubing.
Okay, so you're sticking the bit of, it looks like a kind of plastic cable, effectively, into the end of your blasting device, and you've got a couple of buttons you're going to press there. So should we do a countdown?
All right.
3, 2, 1. Wow, that was quite a nice noise. I like that one. It's a bit higher pitched. What was going on inside there? Was it similar to the nitroglycerine?
It's very similar. It's a different molecule, but again, it contains carbon and nitrogen and oxygen. And again, the shock wave propagates through the explosive, and as it does so, it causes this chemical reaction to happen whereby the molecule breaks apart and then the atoms recombine to make new molecules, nitrogen gas, carbon dioxide, and that recombination, that formation of new chemical bonds releases energy, and that energy release then sustains that shock wave, which then continues to propagate at this very high speed.
Chris Bishop from Microsoft Research.
So now we know what an explosive is and how they work. The next logical step is to find out more about the damage that they can cause, including to the human body. Explosives researcher Bill Proud is developing techniques for testing how different materials respond to these shock waves caused by a blast. And he even has a device that uses donated human body parts to help understand the injuries that can be sustained in an explosion. Bill and his PhD student David Sorry showed Tom Crawford around their bomb lab.
Here we are at Imperial, or more precisely the physics laboratory, and right on cue here's the man of the hour, Bill Proud. Very nice to meet you, Bill.
Hello.
I'm a bit of a pyromaniac, so I'm itching to get started. Shall we head inside?
Well, on the hottest day of the year, that's a good idea. Okay, so we're going into a laboratory environment, so appropriate safety equipment must be worn. So here's your lab coat.
Oh, it's a little big. Okay, safe as houses. So we've just entered the lab, and it kind of reminds me of being back at high school in chemistry, to be honest. There's lots of cabinets. You can see some things that look like fume cupboards. Oh, and here we go. There's a very long tube-like device, which I assume is what we're going to be firing.
This device, the split Hopkinson pressure bar, it's a device that does compressive loading on samples. Compression meaning you're squeezing them to be shorter than they would normally be. And the kind of pressures we're introducing here are over the time periods of, say, 100 microseconds, so 100 millionth of a second. That doesn't sound like a very long period of time, but that's certainly more than enough time to fracture bones, destroy metal, break ceramics. The advantage of this device is it has a very clean on-off pressure pulse, and that has advantages in making the results easier to analyse.
But when you're looking at ceramics and metals, is that to sort of advise which building materials should be used, what kind of materials should be used in protective equipment, for example?
That's true. We are looking at the human body, we're looking at the thing the human body is in contact with. So if you think of body armour, if you think of clothing, if you think of shoes, all of those have a mixture of combinations of polymers, foams, ceramic faces to buildings, the metals that are used in vehicles.
David has very kindly, or perhaps very stupidly, said that I can have a go at firing this thing myself. So what do I do?
Oh, you just press on the boom button.
I'm a little scared about this, but let's give it a go. Okay, do you think you can count me down?
Firing in 3, 2, 1, shooting!
What you've just heard was the sound of a short metal rod, not too dissimilar to a bullet, being fired along a 1 metre long tube into a series of aligned metal rods. The samples being tested are placed in between these metal rods, where sensors are positioned to record the response of the sample to the blast wave. This is all great fun, Bill, but what do we actually learn from these experiments?
The aim of the Royal British Legion Centre for Blast Injury Studies is to understand the mechanisms of blast injury on people, what kind of injury pattern they will get, how to mitigate against that kind of injury, and also to understand the long-term pathology. This means how people recover from blast injury.
And what kind of injuries could occur as a result of a blast?
The human body has a lot of air-filled cavities in them. We're talking about the ears. They're the most blast-sensitive organs we have. Then you get problems with your larynx. But the other and largest and most obvious part of the human body are the lungs. You have conditions called blast lung, where people are exposed to blast wave, and immediately afterwards they feel okay. But over a period of days, their health will decline, and if adequate treatment is not given, ultimately many of them can die. There's also a whole area called solid blast, where metal plates, solid objects, they push on the human body and can produce very severe injuries.
I'm getting a feeling that might be where we're going next.
Yes, you'll be completely right.
So where on earth have you brought us now, Bill? We've been down about 10 flights of stairs through 6 secure doors. What's going on? It's a completely white room, much bigger than the previous lab. Everything looks very clean, and we've been instructed not to touch any of the surfaces.
So we're in the very basement of the Royal School of Mines in Imperial College London, and we're in the room that we house a device called Anubis. And Anubis stands for An Underbelly Impact Simulator.
It's like a rectangle made out of metal girders, and then in the centre of this rectangle is some kind of structure poking upwards, which is housing some kind of large steel drum, which I would assume is the thing that's going to move and cause the blast. Is that correct?
The large steel drum is the pressure vessel, and on top of that there's a metal plate. And that metal plate can be accelerated at velocities of up to 30 meters a second. We would use this for testing what you might call structural components. So that could be, for example, legs.
Do you mean like actual human legs?
Instead of doing studies on, say, animals and then trying to extrapolate that to people, we can do work on human tissues, so yes, human legs, and therefore we can understand directly what the effect is.
By using actual human tissue in the lab, Bill and his team are able to reproduce the same conditions seen in the field, for example in Iraq or Afghanistan. This is verified following an experiment by a military medic with first-hand blast injury experience. During the experiment, measurements are made of the exact forces felt by the human tissue, which along with high-speed video camera imaging allow the scientists to see exactly where and how the bones and soft tissues begin to break and tear in an impact. Pinpointing these locations is key to understanding where the forces are concentrating and therefore where the injuries start. This data can then be used to design protective equipment to try to prevent injury.
All of these human tissues are donated by people when people donate their bodies to medical science, for example, but it's very important that we have that type of material to work with, because this means we can stop guessing of how an animal corresponds to a person. We can know this is what happens with a person.
Yeah, nothing beats the real thing.
In a way, yes.
Oh, I thought they were going to blow up an actual human leg there for a moment. That's Bill Proud and his PhD student David Sorry from Imperial College London.
You're listening to The Naked Scientists with Chris Smith and with Kat Arney. We're talking about the question of explosives and warfare this week and how we can prevent damage to individuals by things blowing up. And so now we know how explosives can cause injury, let's explore what we can do to try and stop it. Well, Cambridge engineer Graham McShane works on materials that are designed to fend off bomb blasts, and actually his work may even prove useful in sport, and specifically the American Football League. Hello, Graham. Thank you for coming in.
Thank you.
What is your approach to doing this?
So the key thing in developing protective materials is to control the forces that are transmitted to the object that you're trying to protect. So when a structure or a vehicle is hit by a bomb or a blast loading, for example, the pressures can get very high. So those kind of pressures can cause a lot of damage. They can cause high accelerations of the vehicle, which can cause the sort of injuries that Bill Proud was just talking about. So the key for a protective material is to mitigate those pressure loads, those forces that are transmitted to the vehicle. Our research is looking at the use of cellular materials to achieve this. So
when you say cellular, can you just explain what that means?
Yeah, so examples of a cellular material are foams or honeycombs. So the materials that consist of an array of cells with solid cell walls, but largely with air gaps in between. And when you crush a cellular material, they deform by the buckling of these cell walls. And that buckling helps to dissipate those forces. So the structure that you're trying to protect feels a much lower force over a much longer time period, which means less damage and less injury.
I suppose the automotive industry kind of know this already because cars are designed to have crumple zones. So when you run into a wall, the car crumples up and it takes time for that to happen. So all of that force and energy is not transmitted straight into the passengers really quickly.
It's exactly the same principle. But really in these cellular structures, we're trying to achieve that at a smaller scale.
You began with metals to do this for boats and things.
That's right. We were interested in protecting ships against underwater explosions where the pressures are very high. So we need materials that are going to be extremely strong and be able to absorb very large amounts of energy. That's why we were investigating metallic steel structures. So we're making honeycombs and corrugated structures out of stainless steel by taking plates of the steel and joining them together by welding and brazing and putting those inside sandwich structures which have solid face sheets outside these cellular materials and then looking at how they can protect the structure against the effects of a blast load.
Do they work?
They work very well. They're able to absorb a lot of energy, but they're also very efficient structures, these sandwich panels. They're very light and very stiff, so they allow you to reduce the weight of your structure as well. The downside is they're difficult to manufacture and they're more expensive.
Can you take the fact that you've worked out these geometries for these materials to dissipate energy in this way and say, well, I'm not going to do it in metal, I'm now going to do it in some new material?
Absolutely. There are a wide range of applications that rely on the same principles. So personal protective equipment, where you're trying to protect people's heads or bodies against impact injuries. But the regime of loading is very different. The forces are lower and so on. So you might want to use different materials. And this is really where 3D printing is coming into its own. So we're able to use 3D printing to make these cellular materials in very complex shapes such that they can fit around the body or around the head out of plastics and rubbers and other softer materials. And we can use the same understanding of how these cellular materials buckle, but apply them in these new applications.
And the connection to American Football League?
Head injury is a big challenge in many sports. American football is one, rugby is another, where people's heads undergo collisions. People get concussions and that can seriously damage their career or put their health at serious risk. So there's a huge range of potential applications for these materials in sports.
So you would take what you're learning in terms of how you're going to mitigate blast to the undersides of Land Rovers, how you're going to mitigate damage to individuals, 3D print rubber materials that could go into, say, a hat or a helmet or something, and that could benefit a footballer, but could equally well, I suppose, find a home on the battlefield.
Absolutely. But there are a lot of challenges in terms of understanding how these shells of cellular materials deform under impact loads.
And I suppose 3D printing must have revolutionised your work, because to knock up those metals, it sounds like that was, well, it's not trivial, it's trying to do that, but if you can 3D print something, you can do lots and lots of different experiments very, very quickly.
Exactly right. So 3D printing gives you a huge flexibility to create a wide range of different geometries out of a wide range of different materials and to produce them very quickly. And so you can produce a one-off. You can experiment with different geometries and different designs. And it gives us real freedom to explore new solutions.
Well, things like Alzheimer's disease, because of repeated head injury, are a big problem in contact sports. So there could be a lot of American football players who have a lot to thank you for in the future, Graham. Thanks very much for coming to talk to us about it. That's Graham McShane. He's an engineer from the University of Cambridge.
It's not only vehicles and sportsmen or women that need protection. Body armour is a key weapon in the fight against explosives. It not only has to protect the wearer, but also be lightweight enough to allow them to do their job effectively. This has led to all kinds of creative solutions over the years, with new exciting ideas like liquid body armour to the use of natural materials such as spider silk. Adam Healy researches this field at the University of Surrey, and he joins us now. What is the kind of body armour that soldiers or police would be wearing nowadays?
Well, the typical kind of armour you see on troops on the ground, if you consider like typical flak jackets they kind of wear, the fabric itself is usually made of things like Kevlar and nylon, very strong fibres. They have pockets in the fronts and the sides and the back into which slot hard plates designed to stop very high energy impacts like armour-piercing bullets and things like that, which are commonly made of a combination of ceramic and composite. There are several advantages that ceramics have over other kind of materials. I mean, for example, one of the main things is weight. Weight for weight, ceramics and composite systems are able to stop higher energy impacts than almost any other material, such as metals. It takes a much thicker metal sheet to stop the same kind of bullets that ceramics can. It's quite difficult to nail down specific material properties that can be linked to bulletproofness, if there is such a word. High hardness is commonly used as an indicator in this respect. Although something else that armour developers are constantly trying to improve is cost. We would try and armour all soldiers with diamond if we could, but it's very, very expensive.
It'd be really blinging, though. So tell me about the kind of work you're doing. You work with ceramics. What's working in their structure to make them protective against high impacts?
The way a common ceramic armour system works is that there's a sheet of ceramic and a sheet of composite. The job of the ceramic is to destroy the bullet, and the job of the composite is to catch all the bits that are left. The ceramic does this in a variety of different ways. It's very hard, so the bullet is fractured against it. As it breaks, it starts eroding the bullet as it pushes through the system. Fragments fly off. They take energy with them. And I'm examining the fragmentation and trying to work out what's actually happened, like how have these fragments formed. Normally when you shoot something, the fragments end up behind the gun that shot it. They go all over the range. But I've been using different methods to capture all the fragments, and I've been trying to characterize these fragments and also look for similarities between fragments generated from ballistic events and fragments generated from other tests that are available to us.
So you're kind of trying to put all this information together to work out almost a prediction of how materials would respond.
Pretty much, yes. It's a very large, fast and difficult jigsaw.
I can imagine that. Where are the ceramics of the future heading in this kind of body armour?
What a lot of people are working towards at the moment are ceramic composites. They've got a solid plate of ceramic and they have different particles in here that change the way the ceramic behaves under impact. Like it might change the direction of cracks or generate fragments in different ways, which will have an effect on how ballistically powerful the material is.
We just heard Graham talking about the issues of flexibility and the kind of ways that he's structuring the materials that he's working on. I mean, with ceramics, presumably they're very hard and not very flexible.
Yes, that's true. Sometimes you hear of soldiers just foregoing those hard armour plates altogether, just taking them out of the flak jacket. Sometimes people try to develop new ceramic plates which are actually made up of loads of little plates, like in a mosaic pattern, but they're not as ballistically strong as like a solid ceramic sheet.
So it's always going to be a toss-up between the flexibility you need and the strength, the hardness to withstand those kind of impacts.
Those are the kind of areas that body armour development is trying to improve on.
We've heard about some new ideas in body armour. There's an idea of liquid body armour. I mean, what would that be about?
I take these kind of developments with a pinch of salt because I haven't found any academic papers on them. But the way it works is that the molecules in these liquids, they rearrange under high impact and they stiffen up. My current understanding is that it can't harden quickly enough or strongly enough to stop bullets. It's mainly used to treat Kevlar vests to increase their stab resistance.
And what about using the natural world as a source of inspiration to inform us with about the development of body armour?
Biomimetic armour, which is armour inspired from structures found in nature, is a very exciting subject. A very interesting paper I read looked at mantis shrimp. They scuttle around, do their thing, and they basically spend their entire life punching crabs to death.
Okay, they're strong.
You can imagine the kind of power behind the clubs that they use to do this and the incessant impacts that they had to do over and over again their entire lives. The materials involved in making those clubs must be excellent at absorbing impacts. So some people are looking into how they do that and seeing whether it can be transmitted into armour applications.
I love the idea that the armour of the future could be inspired by a shrimp that clubs crabs to death. Thank you very much. That's Adam Healy, and thanks also to our other studio guest this week, Graham McShane. And finally, Greer Jackson has been refereeing a heavyweight bout this week as the contenders fight it out to answer John's question.
What is the most expensive element in the world?
It's a hefty title with many contenders and weight classes.
What did you guys think at home, though? Facebook fan Jacob suggested it's oxygen because nobody can live without it, whereas Tam argued that heroin or cocaine should claim the title because it costs so many lives. So how do we define expensive, and what other criteria should we be considering? Chemist Mark Lorch from the University of Hull.
Plenty of materials are extremely expensive. There are drugs such as Solaris, which costs a whopping $700,000 for a year's treatments. And there are chemicals that have high social costs through drug abuse or pollution. But strictly speaking, none of these are elements. They're mixtures of elements bound together, known as molecules or minerals.
Ah, so they're not strictly elements. That narrows down our search just a little. So we're clear though, what exactly is an element, Mark?
Elements themselves are something that can't be chemically broken down into a simpler substance. And of course, they are all nicely laid out on the periodic table, or indeed in song. There's antimony, arsenic, aluminium, selenium, and hydrogen and oxygen and nitrogen and rhenium, etc. So, being a chemist, I'm going to use that definition of an element.
Okay, so we're looking for an element, but what do we mean when we say expensive?
Well, we can't live without oxygen or carbon or a host of other elements, which makes them invaluable. But to make things slightly simpler, I think I'll stick to purely monetary values.
Let the fight begin. Weighing in at just 12 on the atomic mass scale, its lightweight underdog, carbon.
It might cost pennies when it's graphite in your pencil, but turn it into the best diamonds and it might fetch $100,000 for a gram.
Phew, that is a hefty price tag. What else is a contender?
Astatine. It's radioactive with a half-life of a few hours, and so it decays as quickly as it's produced. The result is that there's probably less than 10 grams of naturally occurring astatine on the whole of the Earth. But astatine still isn't the rarest member of the periodic table. Not if we take into account man-made elements. That accolade probably goes to livermorium, made by bombarding heavy atoms together, causing them to briefly fuse into the new element. Only a handful of atoms have ever existed, and with a half-life of 61 milliseconds, they don't hang around for very long either. But whilst these were fabulously expensive to manufacture, there's no commercial reason to do so.
What does that leave us with as our champion?
It's another man-made element, but a useful one, with applications ranging from initiating nuclear reactors to radiotherapy treatments for some cancers. But it doesn't come cheap. You'll need to set aside a cool $27 million for just 1 gram.
And the winner by knockout is Californium. Thanks, Mark, for that scintillating roundup. I hope that answers your question, John. Next week, we lend an ear to Jerry's question.
What acreage of a wheat field do you need to make a large loaf of wholemeal bread?
If you see yourself as a bit of a farmer or indeed a baker and think you know the answer, you can email chris@thenakedscientist.com, find us on Facebook, tweet @nakedscientists, or get stuck into the debate on the forum, nakedscientist.com/forum.
And that is it for this week. Thank you very much to Tom Crawford and Ginny Smith for production. Next week, we're at the BBC's Make It Digital event, which is an exploration of the new forthcoming digital world that we're all going to be living in, and encouraging people to engage with it and showing you some of what it can achieve. If you have any questions relevant to that, you can send them in to chris@thenakedscientists.com. This show comes to you from Cambridge University. It's supported by the EPSRC, the STFC and Rolls-Royce. I'm Chris Smith, and until next time, thank you very much for listening, and goodbye.